My name is Chris Mancuso. I'm a PhD candidate at Laurentian University. My supervisor is Dr. Richard Smith. And the talk I prepared for you today is it's a methods development piece regarding seismic data. Essentially, it's how to extract and use surface wave data from our seismic information to image structures off to the sides of our transects. So one thing to point out is that reflection seismic imaging is very suited for looking at horizontal or low dipping structures in the earth, while it's a little bit weak for looking for steeply dipping structures. And that's where the conventional P-wave, body wave imaging methods start to break down. And as Richard and Mustafa has sort of got into this morning, is that there are seismic zones in our images at different locations. In all of our transects, I would say that the top 1 kilometer are devoid of any structural detail in the seismic imaging, or what we call acoustically silent. And part of that relates to the problem of imaging steep structures. So I've been exploring different ways to try to fill in that gap. So in the past, I talked about integrating other sources of geophysical information, such as magnetics or gravity information, doing joint inversions. Today, what I'm going to talk about is using a different component of the wave field in our seismic data, specifically surface waves, which we often treat as noise, but do provide information on the shear wave velocity, specifically at the near surface area of the Earth, so the uppermost 1 kilometer. So just a quick background on surface waves. So these are confined to the surface of the Earth. They don't radiate down in. They just travel on the free surface, we call it. And this is distinct from body waves. So in all the reflection seismograms that we saw today, those were body wave images using P waves. So I'll be talking about using surface waves, which are sensitive to the shear wave velocity of the Earth. They roughly affect down to 1/2 of their wavelength in the Earth, and they're really high energy. They decay slowly. So as opposed to body waves that decay at the square of the radius, a surface wave will decay at the inverse of the radius. So they go much further, essentially. And they can be roughly explained by 2 different movements. So we have Rayleigh waves and Love waves, and it's just how they're sensed with geophones. However, I find it's a very simplistic understanding of them. There's a lot of conversions and polarizations which make it more of a spectrum. But in general, Rayleigh wave will be sensed in the vertical and the radial components of the geophone, whereas the Love wave will be sensed in the transverse component. And so with regards to surface waves and the method I'm going to talk about, we're going to focus on what's called backscattered surface waves. So a backscattered surface wave most easily could be thought of as sort of a sideways reflection. So in conventional P-wave imaging, we have a source and it sends radiates energy down into the Earth, it hits the top of something, bounces back up, and we see it on the geophone. Well, the same thing's happening with surface waves, except of course they're moving laterally. And instead of impinging on the tops of structures, the horizontal interfaces, they're impinging on the sides or the vertical interfaces. So that's what I have in this little diagram here. Just showing the source radiating energy laterally, impinging on a dike, and then backscattering. Now, if we were to collect a field gather, or what we call shot gather, for this sort of experiment, we have the source and a bunch of geophones in a line like this, what we would see is first our body waves arriving because they're the fastest, followed by our surface waves with linear move out as the offset increases. However, the backscattering would be seen buried beneath those as the latest arrival, but also with reverse move out, or negative velocity in a sense. And so that's what you see beneath here, these arrivals, which are opposed to the surface wave. And I'm just extrapolating them here with red lines just to really point out where they are. Now, there have been some methods developed to use this information to focus on near-surface structures like faults and dikes. And they basically fall into one camp in which imaging uses assumed Green's functions. So they're finding out what the velocity of the Earth is by doing some fancy processing on the waves. What I'm developed and what I'm going to propose in this talk is sort of a precursor method for that, which is very much based on the principles of CMP processing, in which we assume a velocity and then we provide an image to sort of show where the structural boundaries are that are picked up by these waves. Now, with regards to Metal Earth, I think it does fit the project. A lot of our transects and information we're collecting are about the 10 to 100 kilometer scale. And we do seem to have a gap in the uppermost 1 to 2 kilometers in terms of seismic information. With regards to surface waves, our vibroseis energy peaks are around 10 to 30 hertz bands, and that roughly corresponds to our imaging resolution about 100 to 300 meters. So the scale of structures we can image sort of fit within those bounds. Another thing that I've talked about a lot in the past is that there's a lot of arc-like portions in our transects. We have what we call crooked line transects, so a lot of S shapes and curves. And what these do is they actually provide areas of broad azimuth information. So we're kind of getting the ability to image around an area a little bit. And a lot of work in my own master's, as well as some of our PhD students and research assistants, has been to image the 3D structures within these bounds, whether it be using multi-focusing methods, cross-dip move-out, or 3D processing. And then the final thing I'll touch on is just our vibe array. So very quickly, when we collected the data, we used 4 vibe arrays, 4 vibes in an array. This is done to actually suppress surface waves, or what we call ground roll in the data. However, that's true in the inline sense along your geophone arrays. Cross-line to that, they would actually be additive and would actually increase the amount of surface wave energy in theory. And so the bottom line is that our transect bends are most capable of being capable areas for surface wave imaging. Right, so for the method, I developed a migration operator to provide images of, related to the scattering of surface waves, vertical structures. So if you're familiar with migration, in the sense of like Kirchhoff migration is often done, say 2D, it would be distance and depth. The variation on this is that it's done over a plane on the surface, so an X and Y direction, assuming that there is no change in depth, or what we call a constant velocity, and no dispersion of the wave. And I've tested this on synthetic and real data. So verifying first on synthetic, I developed a 3D model in SpecFem 3D. This is a really good program to do this sort of modeling in because it uses what's called the weak form of the elastic wave equation, but that perfectly honors surface waves at the surface, and also allows for topography to be built in your model in a very realistic way. And as an output from that, you can also get density, VP, and VS models from your joint topography. For field data, I experimented with the Gibraltar transect, specifically the southern lib, the R1 data from that. And that's just an area of, that is known to have complex fault networks in a greenstone environment, and has a significant bend in the transect, about 135 degrees, or a third of a pizza. And so here's what my synthetic model looks like on the left here. This showing in plan view. This was discretized into a few thousands of cells, but essentially it's one background area with a few anomalies plotted in. So the reds are anomalously high density, anomalously high shear wave speed, and the greens are low density, low shear wave speed with regards to the background. Now you see this circle is the geometry in which I put all the geophones and sources, so that's the acquisition geometry, and that broadly divides the area into 2 spots. You have your inner geometry and your outer, and I'll say that the inner is our area of interest. And just showing on the side in 3D, this is really just like a plate. You know, it's because we are not going to be able to image too deep into the Earth, so it's only 2 kilometers thick. And this just speaks a little bit more to the acquisition geometry of that ring. So that ring is actually many receivers and geophones in a line, so 200 receivers. They're computed as 3-component receivers. And every 4th one has a source point that's co-located with it. And I chose a frequency of 10 hertz as the peak fundamental frequency for this. So that sort of fits with the energy peaks that we get with our own surveys, and something doable with a vibroseis. Now, with regards to Gibraltar, so Gibraltar, as you know, is located in the western Superior Craton, at the border of the Quetico and the eastern Wabigoon subprovinces. And I'm just showing here on this map just the southern limb of that transect. So that's what this black line is here. And part of it I've highlighted in red. So that red part is the information I used in this survey. And the way that I extracted information is I put a circle of best fit around it from a known point, or from a central point, and to about a radius of, I think it was 8.5 kilometers. And that's what this sort of shaded zone is. So that's just the area, the domain of interest, for instance. And then notable structures in the area are the Bombal, the Tomball Beardmore Fault, which of course is east to west, and which is cross-cut by the Jellicoe Fault. With regards to the seismic information itself, I also decimated it, so I only took every second receiver, and then every fourth shot. That just matched the spacing in the synthetic data. And I windowed it just to 6 seconds. That's about the length it would take for a surface wave to travel from one of those sources to the center and back of that area. And then finally, I just low-pass filtered it to 20 hertz. Now, when calculating the migrated images, that was an opportunity to estimate the velocity, essentially by just making picks and then seeing which velocity gave me the most coherent structures in that. So that's how I estimated velocity with regards to the real data. For processing, for the 3D data, or for the synthetic 3D data, it's 3-component. What I had to do was rotate the components to be what's called local polar basis. So I defined one point in the center, the origin, and then fixed all the radial components towards that, and then the transverse components, orthogonal to that. I also sectorized it, so this is analogous to doing like common midpoint bins, but in this case it's common sector azimuth bins, and I took those in 2-degree slices around there, around the origin. So here's some results. See a couple of wave field snapshots during the simulation itself. On the left at 2, and then on the right at 3 seconds, emanating from the green star. Just one random shot I chose out of this simulation. So the P wave is out here's a little dim, but about half the distance from that is our surface wave. And it's very high amplitude, very circular wave field. And what I do want to point out is that there is very clear in these snapshots where the reflection backscatters are emanating from. So from this first sort of Z-shaped structure, I can see I've pointed out 2 of the reflections here. At 3 seconds, they traveled further, but also they started to impinge on some of the structures outside of the acquisition ring. So as a convention in this presentation, the yellow arrows are reflections from inside the area, and blue is from outside. So field gathers, or common shot gathers from the simulation. And I'm just quickly pointing out on here that they're very clear wave trains from backscattered surface waves, and I've indicated many on there that I'm most confident about. So they stand out very distinctly in the shot domain. And the sectorized gathers, they're also distinct, and their apex becomes shifted to the center. And of course, these windowed offsets very narrow, but they do show in the very near offsets where those sorts of backscattered reflections are evident beyond 4 seconds. So here's the results from the migration algorithm that I developed. So just again, on the top right, I'm just putting a little image of the model domain, just so we can make a comparison. On the left is the radial component, the image process from the radial component, and on the right is the transverse component. The radial seem to have the weakest ability to map these interfaces, whereas the transverse is very clear. So the yellow arrows are pointing to the interfaces that correspond to the various anomalies within the ring, both high and low. And the blue point to sort of smeared or misfocused reflections, which I believe come from outside the ring. And then just on this one, I'm just updating the left plot to show you the Z component, or the vertical component, which is actually very similar in character to the transverse component, in that all the edges are reasonably mapped in all the structures within the ring. So the transverse and Z components seem to be the most sensitive to this. What that says to me is it's very sensitive to love waves, and we have love wave energy in this, but possibly polarized Rayleigh waves. And however, that's because we only have the Z component, and we're missing the radial component of the energy. The in-ring structures were focused, and the outer ring structures were defocused due to destructive interference. The ring geometry is actually very favorable for imaging these by providing that sort of focusing. And of course, this was limited just to a finite frequency assumption and just one constant effective velocity, which is obviously not true of the real world. Now, with regards to real world, here's the information from the Gibraltar transect. On the left, I'm showing one common shock gather. On the right, one of those common azimuth sector gathers. The white arrow points to what I can identify as backscattered surface waves. And again, on the right here, one area, one package of what I believe to be backscattered surface waves when you put it in arc length coordinates and move it out. And here's on the left is the migration image from the Dralton. Now remember, this only had 135 degrees of azimuth, so we're only getting a third of that pizza. But it seemed to have some sufficiently coherent reflectors in there that I was confident to pick. 3, in fact. So 2 up here to in the northeast quadrant that trend about 135 degrees, and then 1 in the southeast quadrant that trends at about 60 degrees. And just to put that in perspective, I overlaid that onto the geology, and so I'm just kind of carrying over the geological contacts from the various units mapped on surface in this image, and as well as the faults. So the 2 in the northeast quadrant, they appear to terminate at the geological fault, and they appear to be orthogonal to its strike. The southern one appears to correlate with a specific jog in the Tombo-Beardmore fault along its length and its direction. I've also compared magnetics to help try to increase my confidence in these picks. So I'm showing on the right is just a magnetic relief map. It's essentially just a derivative. This is showing where the main things are located without indicating their strength. But that's really good for pointing out dikes and faults and offsets. And so, and I've carried over the interpretation information I made from each of those areas onto this. Now, maybe a little hard to see in this image, but these 3 do correspond to this one localized magnetic high, which terminates at the geological fault. And I believe the third one actually offsets a small dike that's located in there. I've convinced myself of this. Hopefully I convinced you too. And on the bottom here is that same jog that's of the Beardmore-Tombo fault. So as a result of this, I estimated the surface wave speeds from picking different constant effective velocities and testing the image, and I estimated to be 3,500 meters per second, and that is typical of crystalline rock. So there's a question that comes to mind is whether I'm imaging the overburden or the actual near surface rock. Well, this would seem to fit that we're measuring rock in this case. The paired reflectors in the northeastern quadrant, they are related to the geological fault and its offset, and my thought is it's probably related to transpression, or maybe it's some sort of silicified zone. It's also indicated by the magnetic imaging. And then the Beardmore fault captured in that one small jog. The information we extract from that is that jog would have to be very steeply dipping in order to be imaged by this method. As regards to the method and the information we had on hand, I can conclude that we have sufficient trace fold and just that one little bend of the Dralton transect for migration, despite there being limited coverage. And of course, in the real data situation, we're limited to the Z component because that was the information we collected as opposed to 3 component. But the Z component does appear both in synthetics and in the real data to be quite sensitive to the surface wave backscatter that we're modeling. So in conclusion, I would like to say that I think that this is an efficient 2D trace migration. It would be a precursor to the more advanced methods like reverse time imaging or what's called natural migration methods. And it's tested under certain limitations or assumptions, the finite frequency assumption and of course the constant effective velocity assumptions. It seems to be most strong in areas where there's arc or bends in our data. So the bends in our transects provide that sort of focusing for structures within those bends. And using that information, we're able to image some parts of steeply dipping structures within there, using only the vertical component information again. So there's a lot of future directions I think that this could go. One of the things I need to look at immediately afterwards is maybe building on the constant effective velocity assumption, maybe seeing if I could make more laterally variant velocity models. And maybe that would start with this, comparing the stacking velocity approach I took to maybe a semblance approach. Again, borrowing from the CMP processing manual. I'd like to carry this over to a joint tomography, and at least with the synthetic data. So the good thing with the work I've done here is actually good information to help parameterize those models. So a lot of workflow that goes into full waveform inversion imaging and reverse time imaging and joint tomography or whatever you call is actually selecting the component of the wave field that you want to image. And it often involves time cuts. And so being able to actually analyze the move out and the azimuth of the reflecting events, we can actually sort of more finely tune those methods. So this provides actually good precursor information for doing that sort of work. I need to continue to compare the ring geometry with more conventional 3D patch or line-based versions. I've started that process. And I'd like to test this at different scales, including archaeological scales. And finally, the ultimate would be to collect full 3-component field data and in full azimuths. And that's it in my presentation. I'm happy to take any questions.